Then let's start our first lecture, Quantum Mechanics 130B, Part 1, Matrix Mechanics. Okay, so, so as introduction, I want to say, well, what is matrix mechanics? Matrix mechanics is another alternative way of formulating quantum mechanics in terms of linear algebra. And the most basic object in linear algebra is a vector. I want to propose this slogan called "everything is a vector," which is actually very popular, not only in physics nowadays, but also in computer science, in particular, machine learning and deep learning. So, so actually, quantum mechanics takes the same strategy as machine learning in treating information, in encoding information. So what is quantum mechanics? Quantum mechanics, maybe we all know, it's a physics theory describing behaviors of quantum systems. So typical quantum systems is like microscopic particles like electrons and atoms, and maybe inside the atom you have nucleus, maybe you have fundamental particles like quarks and leptons or gauge bosons, so these particles. There's also strings. Strings are the quantum particles or quantum objects that describe quantum gravity. And then there's also qubits. Qubits is called, it basically full name is quantum bits. It's the fundamental units that people use to do quantum computation. So all these things can be described by quantum mechanics as a physics system. And then as a physics theory, quantum mechanics, what does it need to do? So in general, on a very high philosophical level, any physics theory need to have two abilities. One is the description power. The other is the prediction power. As description power, a physics theory must provide a description of the physics system. Of course, you can describe physical systems, the state of a physical system, in terms of words, language, right? For example, I'm standing still here. I can say my state of motion is like I'm just standing here. Or you can be more precise using like my momentum is zero, for example. So momentum being zero is a description of the state of the system as myself, as my body. So any physics theory need to provide such a kind of description. And then based on the description, it must also provide a prediction of observables, meaning that if I try to measure my state of motion, I should see or I should confirm that my momentum is indeed zero. And then I should also be able to predict my dynamics. That means if I just put the system there and let it evolve in time, after a while, I look at the system again, maybe I will get a different observable. The observable may change in time, so I want my physics theory to also make that prediction. So basically, the goal is to encode the state in some state variables, and then based on the state variable, make prediction about observables and dynamics. And that's three things. State, observable, and dynamics is the three things that we will talk about in part 1 about quantum mechanics. We will see how quantum mechanics was able to do that. As a physics theory, it's all about encoding physical reality, which correspond to observable and dynamics in the form of information. And information is encoded in these state variables, in these variables that describe the states. So it's all about information. And as we want to describe the state of the system in terms of some state variables, we are basically encoding the information about the system in some variables. And then the choice of state variable is not unique sometimes. And then the state variable itself may not have physical meaning. I should emphasize that there is a distinction between classical and quantum mechanics. In classical mechanics, we use the same variable to describe the state and also describe the observable. For example, momentum is an observable because you can measure momentum in the lab, or you can measure position in the lab. And you are also using position and momentum to describe the state of a classical particle. This is no longer the case in quantum mechanics. In quantum mechanics, there's a separation between the description of the states, for example, using wave functions, and then the observables, which still correspond to position and momentum. So you don't directly use what you can observe to describe the system. Instead, you use something very abstract, like wave function, which has no physical meaning, which can even not be measured in the lab. No one can measure wave function in the lab. Wave function is a concept that's only being inferred from the observation. So you observe the momentum or position of certain particle, and you infer what kind of quantum state or what kind of wave function it is that describe this quantum system. So there must be a separation between these two. So I think if you realize that, that will maybe cure some confusions. So state variable, like wave functions, does not need to have physical meaning. So don't ask me what's the meaning of wave function. For now, we will see that later. So here is an example where you can have multiple different ways of describing the same amount of information, maybe. So I'm showing you pictures of, so these pictures, okay? So these are called MNIST data sets used in training machine to write digital numbers. So as image files, every single picture as image file, you can either encode the information in terms of the brightness of every pixel. This is basically using all possible observables to describe an image. But sometimes this kind of description is very redundant and not very efficient, because in order to describe every pixel, and you need a large file, basically. And then these pixels are also highly correlated in the sense that if you look at all these pictures, all the edges are blacks, right? So you're wasting your space to describe those pixels, which is always black, and then it's not going to encode any information. And then pixels are correlated in the sense if you write the number 1, if you have a bright pixel up there, the bright pixel will continuate it downwards, right? So all these bright pixels must be correlated together in order to form a line. Otherwise, the digit doesn't make sense. So, that means in some sense, that means there's a separation between the description of the state and the observable. You can observe many things about the system, but maybe that that's not a good description. Maybe there's a more efficient description. Like as human, we will describe these pictures by digits, 1, 2, 3, 4, and so on. So that's describing things by names. But if you describe things by names or by language or by words, sometimes that's okay, but sometimes it's not very precise. Although it's very efficient, but not very precise, because there's many ambiguities in human language. So there comes the third method, which is machine learning. What machine learning does is basically it uses a neural network to encode all these pictures into a latent space. A latent space is an imaginary space, is a vector space, where every image basically gets encoded as a vector. In this case, as a 2-component vector. And the 2 components correspond to the coordinate of this image in this latent vector space. There's a horizontal component and vertical component. The meaning, physical meaning of this component may not be clear because it's up to machine to learn. And then they basically correspond to certain features in these images, such that when you aggregate this image in this latent space, you can see similar image will appear in similar positions because they have similar features. So this is what machine learns. And machine basically, this kind of a vector encoding is both efficient and precise. Because it compresses the information, but it also avoids certain ambiguity in human language. So that is how machine learning scientists nowadays is used to describe images in our AI models. And that is exactly the same strategy as quantum mechanics. Quantum mechanics describe quantum system, the state of a quantum system, using vectors by encoding quantum states in the latent space, in certain vector space. So the meaning of this vector space may not be clear at this moment, but we will explore more of them later. In quantum mechanics, every state is described by a complex vector, and then the state vector, this vector is called the state vector. By complex vector, I mean the vector components are all complex numbers. And then the vector components are the so-called state variables. They may not need to have physical meaning. They are called probability amplitude or wave amplitude in the literature, but I'm not going to explain what is waving here because really they don't need to have physical meaning. And then this particular vector-based approach, as I said, is just one way to describe quantum mechanics. There are many alternative ways to describe quantum states because the way you choose to describe the system, it's like a language choice. It's not unique. There are density matrix description, which is matrix-based. There's classical shadow formulation, which is probability-based. There's quantum bootstrap, which is observable-based. We're not going to cover all of this. In this lecture, we will stick to the simplest state-based, vector-based description using state vectors to describe a pure state of a quantum system, which turns out to be both a simple and efficient way, and then it's a good starting point. So we will stick to that. And then the information that has been encoded in the state vectors is called quantum information. And then it is the foundation for us to do quantum computation and quantum communication and quantum information processing. It's all based on the fact that a quantum state is described by a vector. Vector has a bunch of components. These components are like variables. They encode informations. And you can process this information to do something useful. OK. Any questions at this point? OK, so since we are talking about vectors, let me first review what is a vector. Maybe you have already learned vectors in high school physics or in your previous courses. There are several interpretations of vectors. One way to think about a vector is called a geometric interpretation, which consider a vector, maybe in high school physics, is like an arrow which has both a magnitude and a direction, right? So for example, this is a displacement vector in two-dimensional space. And then that describes how the particle displaces in two-dimensional space. As a vector in two-dimensional space, it has two components. And the two components correspond to the horizontal and vertical displacement. And vector basically also points to a point in the two-dimensional vector space. If you are using Mathematica notebook, you can drag this vector along, and then you can change it to other vectors. So that gives you an intuition. When you move these vectors, basically its component changes. So these components, as two real numbers, encodes the information about this vector. There's also another way to understand vector, which is called the algebraic interpretation, which is the way that we understand vector in computer science, not in physics. Okay, in computer science, vector is just an array of numbers. It doesn't care. It's basically correspond to a data structure, which is used to store and represent information. And then it doesn't need to have this idea of either magnitude or direction, for example. You can describe something like a color vector. Color vector is a three-component vector we used in computer system to describe a color. When you see a slide like this here, when you see all these colors, behind these colors, actually, every color is represented by three numbers correspond to the red, green, and blue value of that pixel. So, for example, this color means that you have 1 unit of red, half unit of green, and a quarter unit of blue. If you mix them together, blend them together, that becomes this orange color. So when you say, I want to describe different colors, then different colors is described by different vectors. I'm giving you two examples here. So for these vectors, definitely, it doesn't make too much sense of talking about its direction. Although it's a three-dimensional vector, but you shouldn't think about it as an arrow in a three-dimensional space. It's better to think about them as an array which contains three components. So that's what we call algebraic interpretation. And that's also the same as word vectors, which is used in natural language processing. We have all been using ChatGPT a lot nowadays. So this is basically based on natural language processing, which is a large language model. So the way that ChatGPT understands our questions is basically it encodes every word in our language into a vector in a latent space. And then after training, at the beginning, of course, machine doesn't know how to encode words in the vector space. But after training, it comes up with a kind of encoding. And interestingly, this encoding actually reflects some kind of concept that was hidden in human language. For example, people found in this reference, you can click that if you're using Mathematica notebook, and then in this reference, people found that after learning, machine actually learns to encode these 4 different words, man, woman, king, queen, in a latent space as vectors, and then it turns out that the difference between man and woman and difference between queen and king by vector, you can minus 2 vectors with each other that calculates the difference or displacement, right? So that difference turns out to be the same. So that means you can not only saying that, okay, this vector is just a bunch of numbers that encode these words. This vector can really be used to do algebra. You can really take the king vector minus the man vector plus the woman vector, and that gives you the queen vector. Okay, so that's an example that people discover in computer science. And then in terms of vectors in quantum mechanics, I should say, among these 2 kinds of interpretation, geometric interpretation as an arrow, and then the algebraic interpretation as an array, quantum mechanics takes the second interpretation. When we talk about state vector in quantum mechanics, it's really just an array of complex numbers. Yeah, that's it. And then there's no directions, there's no need to think about its magnitude. So if you have this kind of mindset, you liberate yourself from thinking vector is always an arrow and try to ask, what is the meaning of this arrow? So don't ask that question. So just think of it as a data structure that encodes data. So as a vector, it depends on its component. We have 2 kinds of vectors, real and complex vector. Real vector is an array of real numbers. Every component in the real vector is a real number. Like you can have an uncomponent real vector. Every number is a real number. And then this uncomponent real vector will, the space of uncomponent real, what does it mean by space? Meaning that you can have a lot of vectors, all possible uncomponent vector, all together form a space. And then that space is denoted as r to the power n. And this power n means that I have n component of real numbers. So any vector that has n real component belongs to this vector space, denoted as r to the power n. R stands for real set, basically. And then there's also complex number. The idea is very similar. It's just an uncomponent array where every element, unfortunately, now belongs to a complex number, and people denote that vector space as complex to the power n. So these you should think are just data of arrays of different data types. In computer science, we have integer type, real type, complex type, and things like that. So it's just that kind of idea. And then the reason that quantum mechanics insists to use complex numbers to encode information is because there's some convenience. In particular, as we will see later, this complex data structure allows us to describe wave behavior and interference, quantum interference, which is a very common phenomenon in quantum mechanics. That's why people stick to complex vectors. Okay? So this is a brief introduction of the idea of vector. Try to make sure that we are on the same page, that this vector really doesn't have meaning of direction and magnitude. Instead, they are just data structures, array of numbers. Okay, so in terms of complex vectors, we have been talking about complex number. So many of you maybe already learned complex number in high school, but anyway, let me recap. What is a complex number? So a complex number is made of 2 real numbers. X and Y are 2 real numbers. They can combine into a complex number Z by multiplying X with the real unit, which is 1, and multiply Y with the imaginary unit, which is the square root of -1. For example, you have X and Y. You can write Z as a linear combination of X and Y with this real unit, which is 1. Then you don't need to spell it out. And then there's an imaginary unit, which is I. I is like the square root of -1. So the real and imaginary unit obeys the following multiplication rules that 1 times 1 is 1, 1 times I is I, and then I times I, that's the only non-trivial rule, is I times I is -1. So that's a very peculiar number. So this number is any real number, if you square it, is going to be positive. But for imaginary number, for this imaginary number I, you square it to -1. So as complex number, you can add them together. For example, if you have two complex numbers, z and w, and this is the addition result, basically you add the real part together and add the imaginary part together. This x is called the real part, y is called the imaginary part. And then you can also have complex number multiplication. If you multiply them together, you just put these two complex numbers together and expand this multiplication through the summation, through the addition. And then you use these multiplication rules of all these units. You can show that, for example, if z and w are these two complex numbers, they multiply together is this result. And then complex number can also have an operation called complex conjugation or complex conjugate. You have a z, which has a real part and an imaginary part. The complex conjugate of this complex number is another complex number which has the same real part and opposite imaginary part, meaning that the imaginary part gains a minus sign. So if you add the real and if you add the complex number and its complex conjugation together and then divide by 2, you can basically extract the real parts, because if you add these two numbers together, the imaginary part will cancel, right? So you basically get twice of the real part, and if you divide by 2, you obtain the real part. For the same reason, if you subtract this number from this complex number with that complex number, you will cancel the real part, and then you will leave yourself with the imaginary part. So these are the two different ways to extract real and imaginary parts in complex number. So the take-home message, essentially, complex number is two real numbers combined with real and imaginary unit. You can use complex conjugation to extract its real part and imaginary part. It supports algebraic operations like addition and multiplication. Let me teach you a little bit about Mathematica, which is the system we use to write these lecture notes. Mathematica is a very powerful, like a computer algebraic system, and then it allows you to do many computations that you don't need to write the program. It's very simple. So imaginary unit in Mathematica can be typeset by ISK, I-ISK. So if you, for example here, if I press a ISK, it will go to like something like that. If I press a I, and then if I press a ISK, oh sorry, maybe ISK II, sorry, ISK II, ISK, yes. So it will become, that's wrong, so you need to type twice. And then this base notation means 3 plus I1, which is a complex number, which is 3 plus I. And then you can also do multiplication in Mathematica. You can say 3 plus I and 4 plus 2I. If you multiply them together, and then the way you do that, if you type this in Mathematica, you press Shift and Enter together, Shift and Return together, then it will give you the result. So instead of doing these algebras by yourself, you can always use these computational tools to do the algebra very conveniently. For example, complex conjugation can be done by a function which is called conjugate. And then you can extract the real and imaginary parts using these two functions. Like that. Yeah. Okay, so everything's fine. Complex number has another very important representation, which is called the polar representation, which is something I want to emphasize. Through Euler's formula, Euler's formula is like e to the I theta is cosine theta plus I sine theta. So this is Euler's formula. And then you just take that. So every complex number can be written in this form using this formula, in the sense that if you have a complex number, because it contains two real numbers, right, x and y, so you can really think a complex number as a point in a two-dimensional space where the coordinates correspond to x, where the x and y correspond to its x and y coordinates. So a point in two real dimensional space is a complex number. And this point has a distance from the origin, and that distance is called the absolute value or the modulus of the complex number. And then there's also an angle which describes these points. What's the angle with respect to the x horizontal axis? So a complex number, you can decompose it into this horizontal component and vertical component. But then using this Euler's formula, hopefully you can see that But if you don't, it's basically on the screen. You can recombine this cosine and sine into e to the I theta. So that's another way of describing complex number. That's like a polar coordinate system that describe a point in a two-dimensional plane by two variables. One is this angle theta, the other is the distance of this point away from the origin. And the advantage of using this kind of description, let me remind you that this distance is called complex modulus, which is given by the square root of x squared plus y squared. And then the theta is called the complex argument, or people sometimes call it phase, and magnitude in physics, that's fine. So if you multiply a complex number by e to the I phi, that basically rotates the complex number by an angle phi. So for example, if I have a complex number which was already written in this polar kind of a representation in terms of its magnitude and its phase, now I want to multiply this complex number by a new complex number which is written as e to the I phi. What happens is that this e to the I phi simply combines with the e to the I theta, and then, you know, if you multiply two exponential function, the exponents basically add together, so theta gets added by phi. But theta basically describes the angle of this complex number with respect to the horizontal axis. Once it gets added by phi, that means the complex number actually moves in the complex plane, which is this two-dimensional plane. It rotates around the origin because its amplitude doesn't change, right? Its magnitude doesn't change, meaning that it's on the same distance to the origin, but its angle rotates. So multiplying a complex number by e to the I phi basically implements a rotation. For example, if I multiply a complex number by I, that actually implements a 90 degree of rotation. The reason is that I, as an imaginary unit, exactly is also a complex phase, which you can rewrite I as e to the I pi over 2. I basically corresponds to a 90 degree kind of a rotation, right, phase angle. So if you multiply every complex number by I, you will rotate the complex number in the complex plane by 90 degrees. That's one intuition. So if you multiply by arbitrary e to the I phi, it implements a phi angle rotation. And if you have two these kind of factors, e to the I phi 1, which rotates the complex number by phi 1, and e to the I phi 2 rotate by phi 2, if you multiply these two numbers together, that corresponds to a new number, which you can multiply that to a complex number in order to rotate the complex number by phi 1 plus phi 2. So each number corresponds to an operation, phi 1 or phi 2 rotation. If you multiply them together, that corresponds to the combined rotation. And then if you want to express the idea of inverse rotation, for example, you can rotate complex number in a counterclockwise manner, which is the ordinary manner. You can also rotate it in a clockwise manner, in the opposite way. And then that basically corresponding to, you want to take this factor and take a complex conjugate. So if e to the I phi will rotate the complex number by angle phi, then its complex conjugate, which is e to the minus I phi, will rotate the complex number by minus phi. That's the idea. The reason that the complex conjugate of this number is that one is because complex conjugate basically what it does is it go and search for imaginary unit. And whenever it sees an imaginary unit, it just attach a minus sign to the imaginary unit. So that's how you can do that. If you want to learn more about all these intuitions, why all this complex number has anything to do with rotation, watch the YouTube video, which is in the lecture notes, which is a very good one. Yeah. Okay, so questions about complex numbers? Yeah, hopefully we learned how to add and multiply complex number. We also learn complex number has an interesting polar decomposition. And then in this decomposition, it's very convenient to describe rotation of complex number in the complex plane with respect to the origin. And then rotation can be implemented by these phase factors. And these phase factors, once they multiply with each other, they compose the rotation, or when they complex conjugate, they basically inverse the rotation. Yeah, if you do I times I, then that is minus 1. Minus 1 is the number that corresponds to 180 degree rotation because it flips every number to its opposite. which is 180-degree rotation. Okay, so with that, let's review another subject, which is called linear algebra. The first lecture is all about reviewing math. Sorry for that, but I think that's important. So linear algebra is basically about matrix and vectors. So let me talk about matrix. We just talked about vector is an array of numbers, and matrix is just two-dimensional array of numbers. That means, for example, here is an example of matrix. You have a two-dimensional array where it's labeled, every matrix element is labeled by the row index and column index because it's two-dimensional, so it has rows, different rows, and multiple rows, multiple columns. So the row index goes, for example, from 1 to m. There are m different rows. And then the column index may go from 1 to n. There are n different columns. And then every matrix element, that's just considered the most general case. Every matrix element is a complex number because real number is just a subset of complex number, right? So if we understand complex number linear algebra, there's no difficulty to specialize that to real numbers. So in the following, I will always assume every number we encounter by default is a complex number. And then m row, n column matrix, the space of all these kind of matrices will be denoted as complex number to the m cross n power. So that means this space contains all these kind of matrices, and then it basically is composed by a complex number. And how many of them? You can just m times n. There are m times n complex numbers in this matrix. There's a special case when m is n. M and n correspond to the number of rows and number of columns. If the number of row and the number of column is the same, then the matrix looks like a square because it has the same number row and number column. That's a square matrix. And in quantum mechanics, we typically only deal with square matrix. So don't worry about those rectangular matrix. So we will always talk about square matrix, almost always in quantum mechanics. Okay, so vector can be viewed as a special case of matrix because matrix is a two-dimensional array. But if one of the dimension only has one like a component, then it basically reduced to a one-dimensional array. For example, you can have a matrix which has multiple rows, but there's only a single column. Then it looks like a one-dimensional array, right? So this is called a column vector. Column vector is a vector which only has a single column. And then there's another vector which is called the row vector. Row vector is also a one-dimensional array of numbers, of complex numbers. And then it's a single row multi-column matrix. You can think about that. So vectors are just special case of matrix. So in the following, if we learn how to multiply, for example, matrix together, those matrix multiplication rules automatically applies to these vectors. And then these column and row vectors are denoted as a Cn times 1 or 1 times n. They are both equivalent, or in the sense that they have the same amount of component as just a c to the power n vector. So why do we need to distinguish column and row vectors? Previously, we say that the purpose of introducing vector in quantum mechanics is just to introduce a bunch of numbers to encode the state of a quantum system. In terms of encoding information in n different complex number, it doesn't really matter whether we arrange this number in a row or in a column, right? Because they are all the same n different numbers, and that's it. But when it comes to certain matrix vector multiplication, as we will discuss soon, there will be a difference between row and column. So that's why, in general, a vector, you can think of it as just n numbers. But when you really want to emphasize that this vector is a row vector or a column vector, we use two different symbols. One is, if it is a column vector, we use this symbol, which is called a cat. If it's a row vector, we use that symbol, which is called the bra. And then this is called the Dirac notation. We will talk about that more later. But if you ever seen this funny notation in our lecture notes, just tell yourself, this is just a column vector whose name is V. So this V corresponds to the name of the vector. And then if you want to say this vector is a column vector, you just enclose this name by this horizontal and then this bracket kind of notation. And it depends on the orientation of the bracket. There's a column vector and row vector difference. How to memorize this kind of left and right? One way is that you can think about column vector as a mapping from a one-dimensional space to an n-dimensional space. So basically, it expands the dimension of this vector of this space. So that's why it goes like this. If you read from right to left, the vector, basically this pointing brackets basically start from a point, right? It expands into a horizontal, vertical vector. So that's the idea of a column vector. Row vector basically correspond to a mapping that summarize n-dimensional space and map it back to a one-dimensional space. So that's why it shrink the space dimension. So that's why it goes in the other way. That's one way to memorize it. Okay. Yeah?
Why is the row vectors constant?
This is a convention. so when you write down the row vectors, of course you can say the row vector component are still a bunch of complex number, but when we talk about the row vector that correspond to this column vector, actually they are related by transpose and complex conjugate, turns out. Yeah. But if they are not related, they are independent row vectors, you can forget about this complex conjugate. They are anyway just a bunch of complex numbers. Okay, so we will talk about this duality between row and complex vector later. But for now, let's talk about some basic algebraic properties of matrix or vectors. I will just talk about matrices because vector is anyway just a special case of matrix. So for example, if I have two matrices, A and B, both are complex matrix of m row and n columns, and then I may have two complex numbers, alpha and beta. What I can do with these matrix and numbers is I can linearly combine the matrix with this complex coefficient. So I can combine A matrix and B matrix together by multiplying A matrix with alpha, B matrix with beta, and add them together. The result of this combination is still a matrix. So this is still a matrix in the same space. So this is the fundamental defining property of a matrix. When people ask you, like a mathematician asks you, what's the definition of matrix? Matrix is whatever algebraic objects which has this property, linear combination property, that any two matrices in the same matrix space, you do arbitrary linear combination, the result is still a matrix in the same matrix space. That's called the linear combination property of the matrix. And linear combination can be decomposed into two types of more basic operations. One is called the scalar multiplication, which is how you multiply a complex number on the matrix. The other is called addition, which is after you multiply things together, how do you add them together? So let me explain these two operations one by one. First of all, the scalar multiplication is done in this way. Suppose you have a matrix, which is a two-dimensional array of numbers. Now you have a new complex number, which is alpha. Alpha is a single number. It's not a matrix. So you want to multiply this single complex number alpha to a matrix, which is capital A. What happens is that every matrix element gets multiplied by this complex number. So in terms of a formula, I can say that the result of multiplying complex number alpha to this matrix, where the result is still a matrix, right? So because it's still a matrix, so I can talk about its i's row and j's column component. Its component is simply related to the previous matrix i's row and j's column, followed by a multiplication of the scalar vector, scalar quantity, scalar number, basically. So that's called the scalar multiplication. It's very simple. It's just multiply every component by the same number. Just distribute this number into the components of the matrices. There's another operation called matrix addition. The way that we add two matrices together was, is also very simple. If you have two matrices, and then the result of adding them together is simply adding every component, corresponding component, together. For example, the first line, first column becomes A11 plus B11, and so on. So in terms of this notation, it's like A plus B, which are two matrices adding together. The resulting object is still a matrix, so we can talk about its I and J component, which correspond to the Aij plus Bij add together. So scalar multiplication and addition are simple operations. They are all happening on the element-wise level, basically. So all these rules applies to vectors as well, either to column vectors or to row vectors, because vectors are also matrices. The most non-trivial thing comes when you want to do matrix multiplication. Matrix multiplication is a more tricky thing, that you take two matrices and then you can produce a third matrix. And then previously, when we do matrix linear combination, when we take two matrices and linear combine them, they're still in the same matrix space, meaning that the number of rows and number of columns is not going to change. But matrix multiplication is different. Matrix multiplication, you can take matrix from different spaces, meaning that matrix of different rows and columns, and sometimes you are allowed to multiply them together to create a new matrix of another rows and columns. So if you have a matrix of m row and n column, and another matrix of n row l column, and then you can multiply them together, and then that becomes a matrix of m row